In mathematics, the integral of a non-negative function can be regarded, in the simplest case, as the area between the graph of that function and the x-axis. The Lebesgue integral extends the integral to a larger class of functions. It also extends the domains on which these functions can be defined. Mathematicians had long understood that for non-negative functions with a smooth enough graph, such as continuous functions on closed bounded intervals, the area under the curve could be defined as the integral, and computed using approximation techniques on the region by polygons. However, as the need to consider more irregular functions arose, e.g., as a result of the limiting processes of mathematical analysis and the mathematical theory of probability, it became clear that more careful approximation techniques were needed to define a suitable integral. Also, we might wish to integrate on spaces more general than the real line. The Lebesgue integral provides the right abstractions needed to do this important job. The Lebesgue integral plays an important role in the branch of mathematics called real analysis and in many other mathematical sciences fields. It is named after Henry Lebesgue, who introduced the integral. It is also a pivotal part of the axiomatic theory of probability. The term Lebesgue integration can mean either the general theory of integration of a function with respect to a general measure, as introduced by Lebesgue, or the specific case of integration of a function defined on a subdomain of the real line with respect to Lebesgue measure. Introduction. The integral of a function f between limits a and b can be interpreted as the area under the graph of f. This is easy to understand for familiar functions such as polynomials, but what does it mean for more exotic functions? In general, for which class of functions does area under the curve make sense? The answer to this question has great theoretical and practical importance. As part of a general movement toward rigor in mathematics in the 19th century, mathematicians attempted to put integral calculus on a firm foundation. The Riemann integral, proposed by Bernhard Riemann, is a broadly successful attempt to provide such a foundation. Riemann's definition starts with the construction of a sequence of easily calculated areas that converge to the integral of a given function. This definition is successful in the sense that it gives the expected answer for many already solved problems, and gives useful results for many other problems. However, Riemann integration does not interact well with taking limits of sequences of functions, making such limiting processes difficult to analyze. This is important, for instance, in the study of Fourier series, Fourier transforms, and other topics. The Lebesgue integral is better able to describe how and when it is possible to take limits under the integral sign. The Lebesgue definition considers a different class of easily calculated areas than the Riemann definition, which is the main reason the Lebesgue integral behaves better. The Lebesgue definition also makes it possible to calculate integrals for a broader class of functions. For example, the Dirichlet function, which is 0 where its argument is irrational and 1 otherwise, has a Lebesgue integral, but does not have a Riemann integral. Lebesgue summarized his approach to integration in a letter to Paul Montel. I have to pay a certain sum, which I have collected in my pocket. I take the bills and coins out of my pocket and give them to the creditor in the order I find them until I have reached the total sum. This is the Riemann integral. But I can proceed differently. After I have taken all the money out of my pocket, I order the bills and coins according to identical values and then I pay the several heaps one after the other to the creditor. This is my integral. Source. The insight is that one should be able to rearrange the values of a function freely, while preserving the value of the integral. This process of rearrangement can convert a very pathological function into one that is nice from the point of view of integration, and thus let such pathological functions be integrated. Intuitive interpretation. To get some intuition about the different approaches to integration, let's imagine we want to find a mountain's volume. The Riemann-Darboux approach divides the base of the mountain into a grid of 1 meter squares. Measure the altitude of the mountain at the center of each square. The volume on a single grid square is approximately 1 square meter times, so the total volume is 1 square meter times the sum of the altitudes. The Lebesgue approach: draw a contour map of the mountain, where adjacent contours are 1 meter of altitude apart. The volume of Earth a single contour contains is approximately 1 meter times, so the total volume is the sum of these areas times 1 meter. Folland summarizes the difference between the Riemann and Lebesgue approaches thus. To compute the Riemann integral of f, one partitions the domain a, b into subintervals, while in the Lebesgue integral, one is in effect partitioning the range of f. Towards a formal definition, to define the Lebesgue integral requires the formal notion of a measure that roughly associates to each set A of real numbers a non-negative number μ representing the size of A. This notion of size should agree with the usual length of an interval or disjoint union of intervals. Suppose that f plus is a non-negative real-valued function. Using the partitioning the range of f philosophy, the integral of f should be the sum over T of the elementary area contained in the thin horizontal strip between y equals T and y equals T plus dt. This elementary area is just let. The Lebesgue integral of f is then defined by where the integral on the right is an ordinary improper Riemann integral. For a suitable class of functions, this defines the Lebesgue integral. A general function f is Lebesgue integrable if the area between the graph of f and the x-axis is finite. In that case, the integral is, as in the Riemannian case, the difference between the area above the x-axis and the area below the x-axis, whereas the unique decomposition of f into the difference of two non-negative functions, given explicitly by construction. The discussion that follows parallels the most common expository approach to the Lebesgue integral. In this approach, the theory of integration has two distinct parts: a theory of measurable sets and measures on these sets, a theory of measurable functions and integrals on these functions. The function whose integral is to be found is then approximated by certain so-called simple functions, whose integrals can be written in terms of the measure. The integral of the original function is then the limit of the integral of the simple functions. Measure theory was initially created to provide a useful abstraction of the notion of length of subsets of the real line, and, more generally, area and volume of subsets of Euclidean spaces. In particular, it provided a systematic answer to the question of which subsets have a length. As later set theory developments showed, it is actually impossible to assign the length to all subsets of in a way that preserves some natural additivity and translation invariance properties. This suggests that picking out a suitable class of measurable subsets is an essential prerequisite. The Riemann integral uses the notion of length explicitly. Indeed, the element of calculation for the Riemann integral is the rectangle a, b times c, d, whose area is calculated to be. The quantity b minus a is the length of the base of the rectangle and d minus c is the height of the rectangle. Riemann could only use planar rectangles to approximate the area under the curve, because there was no adequate theory for measuring more general sets. In the development of the theory in most modern textbooks, the approach to measure and integration is axiomatic. This means that a measure is any function μ defined on a certain class 10 of subsets of a set E, which satisfies a certain list of properties. These properties can be shown to hold in many different cases. Integration: we start with a measure space where E is a set, X is a sigma algebra of subsets of E, and μ is a measure on E defined on the sets of X. For example, E can be Euclidean n-space n or some Lebesgue measurable subset of it. X is the sigma algebra of all Lebesgue measurable subsets of E, and μ is the Lebesgue measure. In the mathematical theory of probability, we confine our study to a probability measure μ, which satisfies μ equals 1. Lebesgue's theory defines integrals for a class of functions called measurable functions. A real-valued function f on E is measurable if the pre-image of every interval of the form is in X. We can show that this is equivalent to requiring that the pre-image of any Borel subset be in X. The set of measurable functions is closed under algebraic operations, but more importantly it is closed under various kinds of pointwise sequential limits. Are measurable if the original sequence k, where k consists of measurable functions. We build up an integral for measurable real-valued functions f defined on E in stages. Indicator functions. To assign a value to the integral of the indicator function 1s of a measurable set S consistent with the given measure mu, the only reasonable choice is to set. Notice that the result may be equal to plus infinity, unless mu is a finite measure. Simple functions. A finite linear combination of indicator functions where the coefficients sak are real numbers and the sets sk are measurable, is called a measurable simple function. We extend the integral by linearity to non-negative measurable simple functions. When the coefficients sak are non-negative, we set the convention 0 times infinity equals 0 must be used, and the result may be infinite. Even if a simple function can be written in many ways as a linear combination of indicator functions, the integral is always the same. This can be shown using the additivity property of measures. Some care is needed when defining the integral of a real-valued simple function, to avoid the undefined expression infinity minus infinity. One assumes that the representation is such that mu less than infinity whenever x 0. Then the above formula for the integral of f makes sense, and the result does not depend upon the particular representation of f satisfying the assumptions. If B is a measurable subset of E and S is a measurable simple function, one defines non-negative functions. Let f be a non-negative measurable function on E, which we allow to attain the value plus infinity. In other words, f takes non-negative values in the extended real number line. We need to show this integral coincides with the preceding one, defined on the set of simple functions, when E is a segment a, b. There is also the question of whether this corresponds in any way to a Riemann notion of integration. It is possible to prove that the answer to both questions is yes. We have defined the integral of f for any non-negative extended real-valued measurable function on E. For some functions, this integral ef d mu is infinite. Signed functions. To handle signed functions, we need a few more definitions. If f is a measurable function of the set e to the rails, then we can write where note that both f plus and f minus are non-negative measurable functions. Also note that we say that the Lebesgue integral of the measurable function f exists, or is defined if at least one of n is finite. In this case we define if we say that f is Lebesgue integrable. It turns out that this definition gives the desirable properties of the integral. Complex valued functions can be similarly integrated, by considering the real part and the imaginary part separately. If h equals f plus ig for real-valued integrable functions f, g, then the integral of h is defined by example. Consider the indicator function of the rational numbers 1q. This function is nowhere continuous, is not Riemann integrable on 0, 1. No matter how the set 0, 1 is partitioned into subintervals, each partition contains at least one rational and at least one irrational number. Because rationals and irrationals are both dense in the rails, thus the upper Darboux sums are all 1, and the lower Darboux sums are all 0, is Lebesgue integrable on 0, 1, using the Lebesgue measure. Indeed, it is the indicator function of the rationals, so by definition, because Q is countable. Domain of integration. A technical issue in Lebesgue integration is that the domain of integration is defined as a set with no notion of orientation. In elementary calculus, one defines integration with respect to an orientation. Generalizing this to higher dimensions yields integration of differential forms. By contrast, Lebesgue integration provides an alternative generalization, integrating over subsets with respect to a measure. This can be notated as to indicate integration over a subset A. For details on the relation between these generalizations, see differential form. Relation with measures. Limitations of the Riemann integral. Here we discuss the limitations of the Riemann integral and the greater scope offered by the Lebesgue integral. This discussion presumes a working understanding of the Riemann integral. With the advent of Fourier series, many analytical problems involving integrals came up whose satisfactory solution required interchanging limit processes and integral signs. However, the conditions under which the integrals are equal proved quite elusive in the Riemann framework. There are some other technical difficulties with the Riemann integral. These are linked with the limit-taking difficulty discussed above. Failure of monotone convergence. As shown above, the indicator function 1q on the rationals is not Riemann integrable. In particular, the monotone convergence theorem fails. To see why, let AC be an enumeration of all the rational numbers in 0, 1, then let the function gk is 0 everywhere, except on a finite set of points. Hence its Riemann integral is 0. Each gk is non-negative, and this sequence of functions is monotonically increasing, but its limit as k infinity is 1q, which is not Riemann integrable. Unsuitability for unbounded intervals. The Riemann integral can only integrate functions on a bounded interval. It can however be extended to unbounded intervals by taking limits, so long as this doesn't yield an answer such as infinity minus infinity. Integrating on structures other than Euclidean space. The Riemann integral is inextricably linked to the order structure of the real line. Basic theorems of the Lebesgue integral. The Lebesgue integral does not distinguish between functions that differ only on a set of mu measure 0. To make this precise, functions f and g are said to be equal almost everywhere if f, g are non-negative measurable functions such that f equals g almost everywhere, then, to wit, the integral respects the equivalence relation of almost everywhere equality. If f, g are functions such that f equals g almost everywhere, then f is Lebesgue integrable if and only if g is Lebesgue integrable, and the integrals of f and g are the same if they exist. The Lebesgue integral has the following properties. Linearity. If f and g are Lebesgue integrable functions and a and b are real numbers, then af plus bg is Lebesgue integrable. And monotonicity. If fg, then monotone convergence theorem. Suppose fk, k is a sequence of non-negative measurable functions such that then, the pointwise limit f of fk is Lebesgue measurable, and the value of any of the integrals is allowed to be infinite. Fatou's lemma. If fk, kn is a sequence of non-negative measurable functions, then again, the value of any of the integrals may be infinite. Dominated convergence theorem. Suppose fk, kn is a sequence of complex measurable functions with pointwise limit f, and there is a Lebesgue integrable function g such that fk, g for all k, then f is Lebesgue integrable. And proof techniques. To illustrate some of the proof techniques used in Lebesgue integration theory, we sketch a proof of the above-mentioned Lebesgue monotone convergence theorem. Let fk, kn be a non-decreasing sequence of non-negative measurable functions input by the monotonicity property of the integral. It is immediate that, and the limit on the right exists, because the sequence is monotonic. We now prove the inequality in the other direction. It follows from the definition of integral that there is a non-decreasing sequence of non-negative simple functions such that gnf, and therefore, it suffices to prove that for each n, we will show that if g is a simple function and almost everywhere, then by breaking up the function g into its constant value parts, this reduces to the case in which g is the indicator function of a set. The result we have to prove is then suppose A is a measurable set and Fk, K is a non-decreasing sequence of non-negative measurable functions on E such that for almost all xa. Then to prove this result, fix epsilon greater than 0 and define the sequence of measurable sets by monotonicity of the integral. It follows that for any k, because almost every x is in Bk for large enough k, we have up to a set of measure 0. Thus by countable additivity of mu, and because Bk increases with k, as this is true for any positive epsilon, the result follows. For another proof of the monotone convergence theorem, we follow. Let B a measure space. Fn is an increasing sequence of numbers, therefore its limit exists, even if it's equal to infinity. We know that for all n, so that now we need to establish the reverse inequality. Fix alpha, let phi be a simple function with 0 phi f and let then n is an increasing sequence of measurable sets with. We know that this is true for all n, including the limit. Hence, this was true for all alpha, so it remains true for alpha equals 1, and taking the supremum over simple phi f by the definition of integration in L+. Now we have both inequalities, so we've shown the monotone convergence theorem. For fn plus 1, fn, and fn f.y's, fn, L+, the set of positive measurable functions from x, 0, infinity. Well, with taking limits of sequences of functions, making such limiting processes difficult to analyze. This is important, for instance, in the study of Fourier series, Fourier transforms, and other topics. The Lebesgue integral is better able to describe how and when it is possible to take limits under the integral sign. The Lebesgue definition considers a different class of easily calculated areas than the Riemann definition, which is the main reason the Lebesgue integral behaves better. The Lebesgue definition also makes it possible to calculate integrals for a broader class of functions. For example, the Dirichlet function, theoretical and practical importance. As part of a general movement toward rigor in mathematics in the 19th century, mathematicians attempted to put integral calculus on a firm foundation. The Riemann integral, proposed by Bernhard Riemann, is a broadly successful attempt to provide such a foundation. Riemann's definition starts with the construction of a sequence of easily calculated areas that converge to the integral of a given function. This definition is successful in the sense that it gives the expected answer for many already solved problems, and gives useful results for many other problems. However, Riemann integration does not interact those, e.g., as a result of the limiting processes of mathematical analysis and the mathematical theory of probability. It became clear that more careful approximation techniques were needed to define a suitable integral. Also, we might wish to integrate on spaces more general than the real line. The Lebesgue integral provides the right abstractions needed to do this important job. The Lebesgue integral plays an important role in the branch of mathematics called real analysis and in many other mathematical sciences fields. It is named after Henry Lebesgue, who introduced the integral. It is also a pivotal part of the axiomatic theory of probability. In mathematics, the integral of a non-negative function can be regarded, in the simplest case, as the area between the graph of that function and the x-axis. The Lebesgue integral extends the integral to a larger class of functions. It also extends the domains on which these functions can be defined. Mathematicians had long understood that for non-negative functions with a smooth enough graph, such as continuous functions on closed bounded intervals, the area under the curve could be defined as the integral, and computed using approximation techniques on the region by polygons. However, as the need to consider more irregular functions, a probability The term Lebesgue integration can mean either the general theory of integration of a function with respect to a general measure, as introduced by Lebesgue, or the specific case of integration of a function defined on a subdomain of the real line with respect to Lebesgue measure. Introduction. The integral of a function f between limits a and b can be interpreted as the area under the graph of f. This is easy to understand for familiar functions such as polynomials, but what does it mean for more exotic functions? In general, for which class of functions does area under the curve make sense? The answer to this question has great